the cloud. So we went over all the shortcut rules last time, and with the caveat that we were just knowing the rules for the sake of knowing rules. It's nice to know them, but the calculator will figure out all this stuff for you anyway. All right. So as long, I mean, basically, you got to either know the rules or know where to find it in the calculator, which I'm going to go over again in a couple minutes. Either way, you got to be able to come up with the result. All right. So example 6 on page 35, find the probability that of 5 selected people, no 2 share the same birthday. We'll start with that anyway. All right. So part A. No 2 sharing the same birthday means that all the birthdays, all 5 birthdays are different. All right, all the birthdays are different. All right, which means that the first person can have a birthday unrestricted. It could be any day out of the year. So we'd have the first person, second, third, fourth, and fifth person. The first person, again, could be born any day during the year without any kind of restriction. All right, so it's 365 days available to that person out of 365 days. All right, so that covers everything from January 1st to December 31st. Right, in a non-leap year, we ignore leap years as a thing when we deal with this for probability, because it just makes things a little too complicated. All right, the second person can be born on any day except for the day that the first person was born on. All right, so let's say that the first person was born on January 1st. That means that the second person could be born on any day but January 1st, which means that that person has 364 possibilities added to 365 that are available overall. All right. Person number 2 could be born on any of those 364 days, added to 365 available. All right. The third person can be born on any day except for the 2 days that are already accounted for, which means that there's only 363 days left for that person to be born on. The fourth person could be born on any day other than the 3 days that are already accounted for. And again, it doesn't matter what the 3 days are. It could be January 1st, February 25th, and September 9th. You know, like, it doesn't matter. It's still 3 days that are accounted for. All right. So that tells me that there are 362 days left for the fourth person to be born on, added to 365. And then for the fifth person to be born on any day except for the 4 that have been accounted for. So that brings us down to 361 out of 365. All right. So this is an and situation, because the first person is going to be born on a given day and the second one and the third one. It's not an either or situation. So this would be multiplication. All right. And so we could figure out this product a few different ways. One way would be just straight multiplication. Actually, you could do fraction, multiply by fraction, and so on. Or you could take care of all the numerators in one shot, all the denominators in one shot, and get that result. Or you could use a factorial permutation. So I'll show you all different ways. All right. So the first way, again, 365 out of 365 times 364 out of 365, just hitting the division bar and the right arrow. So type in the numerator, hit the division bar, type in the denominator, hit the right arrow, times 363 divided by 365 times 362 divided by 365 times 361 divided by 365. All right. So straight computation, hit enter or execute or okay. And it'll give us, well, a monstrosity of a fraction, but it'll also simplify it down. Well, not really simplify it, but more so convert it over to a decimal form. All right. So unless you want to write that big monstrosity of a fraction, which is perfectly fine, this is one of the few instances where I would say round it, get a decimal and round it. All right. So 3 significant digits, 0.973. All right.
I have a question.
Yeah.
Could you just add up all the top and add up all the bottom and then divide?
Yeah. We'll multiply all the top. Yeah. And the bottom.
Oh, okay.
But
I couldn't just, yes, I could have just done it that way.
yep.
I have a question.
Sure.
I'm so sorry. When I looked at this initially, I thought that we're gonna, I mean, I know it says multiply, but I would have put the denominator as 365 and add up everything. I mean, it doesn't make sense, but I don't know why I thought that that would be a thing.
Oh, just a single 365?
Right.
Oh, I see. That would be the case if you were adding, because then you'd have a common denominator. But when you're multiplying, you actually just multiply all the denominators.
Thank you.
No problem. So yeah, you can multiply it like this, single fraction across the numerator and denominator, do your multiplication, get the same result. Another possibility would be to use a permutation. All right. So I would say 365 P 1, 2, 3, 4, 5. All right. So for a permutation, it's the number you're starting with and the number of values you want in the product. All right. So this is the start. And this number here is the number of values in the product. All right. Now I would take that would account for the numerator. The denominator, it's just 365 multiplied by itself 5 times. So I would say 365 to the 5th power. All right. So in the calculator, again, the permutation we get in the toolbox. All right. But I'm going to start building the fraction first. So whenever you hit the division, it always puts answer over something, which more often than not is very useful. But in this case, I want to put something specific in the numerator, so I just clear that out or backspace it out. All right, so toolbox. Sorry, I was doing this with a different class earlier. So you go into the toolbox, it brings you pretty much to where you left off the last time you used the toolbox. All right. But if you're using the online version of this, it depends, so the app itself should retain the information just like a handheld calculator would. But if you're doing it on their website, on the NumWorks website, it'll reset pretty much every time. All right. So bottom line is, if it's reset, this is where it's going to leave you. Go on down to probability, combinatorics, and then you see the one that says permute. All right. So this means the same as permute. 365, 5. That's what I'm going to put in the top of my fraction. And on the bottom of the fractions is 365 to the 5th. All right. So I'm going to select this. 365 before the comma, 5 after the comma, and then 365 raised to the 5th power. And then hit OK, and it'll spit out the right answer, 0.973. Before somebody asks the question that would probably be on my mind, which way should we do it? Do we have to do it all the different ways? Is there one way that's better than the others? For this question, it doesn't matter which way you do it. All right, but for the next one, we see where it's 45 people selected at random. 45 people that are selected. That's going to make things a little bit dicey in terms of just straight multiplication. So in that instance, you're going to want to use the permutation. All right, but you could see in every case, it gives you the same answer, 0.973. All right, so that was part A. Part B is kind of more of a mental type thing, because there's really no substantial computation required. Right? It's actually very simple. It's just knowing to do this computation that makes it difficult. All right. At least two share a birthday. All right. So that could mean a few different things, but specifically, I mean, if you're talking about 5 people, it could be the case that maybe the first 2 people have the same birthday. Maybe the first and last person have the same birthday, but everybody else is different. All right. So one example of this. Let me just move this over a little bit. All right. So some possibilities are, I'll use S equals same, D equals different. So maybe it's the first 2 that are the same and the last 3 are different. Maybe the first and the third are the same, but everything else is different. Maybe it's the first and the fourth that are the same and everything else is different, or the first and the last are the same and everything else is different. But it says at least 2 individuals share a birthday. So it could be that there are 3 people that share a birthday. All right. So maybe it's same, different, or same, different, different. Same, different, same. Oh, actually, that wouldn't work. I already got that one. So it would be different, same. All right. And so on. Because obviously this is getting a little out of hand. Because each one of these arrangements, you'd have to account for in terms of the probability. So I'd have to figure out the probability of this outcome, this one, and so on. That's obviously going to be a tall order. All right. So if we take a second to do a little thinking, we could get to the answer much quicker. All right. So if there are at least 2 birthdays that are the same, so at least 2 birthdays, we can interpret that as the same thing as saying they're not all different. All right, because if at least 2 are the same, then you can't say that all the birthdays are different from one another. All right. So whenever we want to find the opposite of an outcome, we subtract it from 1. So the probability of at least 2 the same would be equal to 1 minus the probability that they are all different. All right. And the probability that they're all different is 0.973. We've already figured that out. So that's going to be 0.027. So a very small probability that there would be 2 birthdays that are the same, which is, I would say, in the area of common sense. If you walked into a room with 4 other people there and somebody asked, okay, when's your birthday? When's your birthday? When's your birthday? It would be not impossible, but surprising if it turned out that there were 2 people that had the same birthday. There's only 5 people, so it's contradict each other. Yeah, so that's the thing. The question was, would A and B contradict each other? They're opposites. So one is telling the story from one perspective, the other is the reverse perspective. So in a way, yes, because part B is everything that A isn't, and A is everything that part B isn't. All right. Now, if I tell you that there's 45 people in a room, then and then asked everybody to say what their birthday was, I don't know that I would be surprised if there wasn't a commonality, but it's more likely to happen if you have more people. And in fact, if you had 366 people in a room and asked everybody what their birthday was, the worst case scenario is that the first 365 people all have the different birthdays, right? In which case the 366 person would have to match one of those other 365, right? So it gets to a point where it's guaranteed that there will be a common birthday, but we're not there yet, right? Because in number 7, find the probability that of 45 selected people, at least 2 share a birthday. So what I would do is I'd kind of make this a part A, part B, find the probability that all 45 birthdays are different.
Can I ask a question?
Sure.
Why wouldn't you do 43 and then figure out and then just put 1 twice?
Well, because the issue is it has to do with the ordering, because if you don't account for every possible way in which you could have 40 or I'm sorry, 2 matching birthdays, then it's all over, because it goes back to this idea here. If I were to say, all right, well, the first person, second, all the way to the 43rd person, 43rd, all have the same. I'm sorry, all different. And the 45th, 44th and 45th are the same. That's only one possible arrangement. All right. We'd have to account for the fact that maybe the first person and the second person are the ones with the same birthday. And the 3rd through 45th are the ones that are different. And that's only the second possible arrangement, because maybe it's the second person and the third person have the same birthday, or the 41st and 42nd person. All of those different arrangements lead to different probabilities that add to the sum. All right. So what we would need to do is use the process that we used here to figure out the probability that all the birthdays are different. So that would be the permutation 365, 45. Over 365 to the 45th power. So all I'm doing here is I'm taking whatever I had as the second value, because number of days in the year isn't going to change, right? It's just the number of people that are involved in the permutation, right? So that second number and the exponent go from 5 to 45. All right. Now that's the probability that all the birthdays are different. If I want the probability that there's at least 2 that are the same, then it's going to be 1 minus that probability. So 1 minus the permutation of 365, 45, and then 365 to the 45th power. All right. So, I mean, you wouldn't have to write any of this stuff. That's just for instructional purposes, really just to answer the question that was posed. But, and I'll just resize that. This is the actual computation part of it. All right. And let me actually make a note here. I'll put it here. This is the probability that all 45 are different. All right, which they didn't ask for, but it helps us to figure out the probability that there's a commonality. All right, so in the calculator, I'd go back into my toolbox. Well, actually, even before that, let me do this. So 1 minus the fraction in the toolbox combinatorics permute 365, 45, and then 365 to the 45th power. And so let the calculator do the heavy lifting. It'll give you a decimal, but it should be something that you could work with. Now, if it gets cut off like this happens pretty frequently, just scroll onto it and hit OK or execute, and it'll bring that whole decimal down. It also shifts some things over so you could actually see it. But this is about 0.941 approximately. So I don't want to say it's almost guaranteed, because it still leaves over 5% of cases where the birthdays are all different, but this is getting closer and closer to 1. All right, so let me just show you really quickly. If I did, oh, that's fun. I'm gonna do, hold on. I wanted just this computation. If I did this and I said, what's the probability that if there are 365 people in the room, that all of them would have, I'm sorry, at least 2 of them would have the same birthday. So make this a 365 and make this a 365. It might give an overflow, says undefined, but that's because the number is too large. But this is the case where you're looking at something that's very, very close to 1. All right, and that's because the permutation part of it is very, very close to 0. Right, that fraction. All right, so it gives an undefined because it's really an overflow. But that would be the case where the probability is virtually 1, very, very close to 1, almost indistinguishable from 1. It isn't until you get to the 366th person that you're guaranteed a match. All right, so yeah, that's probably one of the trickiest parts of probability, the combinatorics part of it, because intuitively, well, I'll just say intuition is not always the most useful thing in this aspect of probability, because if you have good probability intuition, that's a different story. But generally what your gut is telling you to do is probably not what you're supposed to be doing. Right. So you have to sort of diagnose and think to yourself, is this something that's talking about arrangements or order being important? And if that's the case, then there's going to be a permutation involved, which isn't the easiest thing in the world, but I tend to be consistent with the types of questions that I ask. So, and we'll talk about the practice test in a little bit, but it's this is an area of mathematics in and of itself. There are entire courses dedicated to just learning about probability. We only tend to learn the probability in this class that's necessary for us to understand the inferential statistics. All right, and so this is kind of like the borderline between what is necessary and what would be just kind of a luxury to learn about. All right. Although I don't know too many people that think learning about probability is a luxury outside of the world of academia, mathematics, and so on. You know, you'd really have to be a math nerd in order to find this stuff. Well, I don't want to be unreasonable. I mean, you could still find it interesting and not know what the heck is going on. You know, that's part of the issue. I can tell you, and it never makes anybody feel any better, but I had a rough time with probability when I was first starting out. Like I took those courses.
That makes
that
me
were-
more nervous.
Yeah, I can understand that. Which is why I kind of keep it simple when it comes to the test. Like I said, I'll show you that later, because there's a lot of aspects of math that I didn't become comfortable with until I started teaching it. And not because I had an answer key in front of me or anything like that. It's because I had to explain it to other people in a way that somehow would make sense. And once you start explaining it to other people, you start, discovering the little gaps in your content knowledge, where it's like somebody asks a nice question and you're like, wait, why does that work? And so you have to come up with a way to explain it. And then that makes it, so much easier. But yeah, it's not something that students typically do, like you go to a person who lives in your household and say, okay, I learned about permutations tonight. Let me explain it to you and see if you understand what I'm talking about. Like that would be a luxury. If you could do that, that would be great. I said luxury like 3 times already, so I'm going to make that the word of the day. Luxury, as in a luxury vehicle, or the luxury of having unlimited time to explore and learn probability. Okay. So that's really the extent of combinatorics, at least for our purposes. So now I'm going to hop on over to page 40, because everything else was something in a video that was discussed. But this question here is a pretty important one, at least in terms of the concept of binomial probability, like understanding why things work the way they do. Right. So I'll take you through the example, and while I do it, I'll explain why it's so important. The 2010 U.S. Census indicated that the true proportion of Americans that were female was actually 50.8%. I'll take it as a typo. We can get rid of the word actually, because I got this from a textbook and it was referring to another problem. So it was like, what do you think the percentage was? And then the follow-up question was, well, it turned out the percentage was actually this. So it doesn't make sense in this context. But yeah, use the information to create a new probability distribution for the gender selection technique question from page 38. Then graph the distribution. And is it still approximately normal? I'm going to just go back to page 38 for a sec, talk about that a little bit, and then we'll just kind of get on to this. All right. So in page 38 or on page 30, I found another typo. It's not page 38. It's page 37. All right. So just kind of going back to this, the scenario involved a company that claimed that it could, well, not guarantee, but increase your chances of getting a child through a live birth of the desired gender. All right. So, this is an old problem. It's like 12 years old. It's related to census data from 2010. So it kind of gives you a sense of, just think about what the world was like back in 2010 and you get an idea. All right. The study was conducted to verify the claim. All right. So they followed this program, and these were the outcomes that led to girls, births that were girls. So the chances that out of 14 births, none of them were girls was 0, or about 0, virtually 0. 1 would have been 0.001. And go on down the line, 7 out of the 14 being girls would be 0.210, and so on. It ended up being a normal distribution. You could graph it, you take a look, you could do a normal probability plot if you want, a bunch of different ways to handle it, but it ended up being a normal distribution, and from a normal distribution, you can draw some conclusions. So that's just a quick rehash of page 37. That was all in the videos that you looked at. The reason why I'm doing page 40 is because I wanted to take you through the approach, yes, but also show you how to do some of this on the NumWorks calculator, because there's a lot of TI references in the videos. All right. So what we want to do is determine if it's unusual to get 11 girls among 14 births. knowing this new percentage, the probability. All right, when they talk about percentages or proportions, it's synonymous with probability. All right, so what this is saying is the probability of getting a female is 0.508. All right. So we would want to use that to make a determination of what all the actual probabilities are that would make up this table. All right. Now you could do it with technology pretty easily. And in fact, it's probably better, it's a preferred approach to use the technology because it makes it very easy as opposed to something that would be complicated if we did it by hand. All right. But first, I want to make sure that I'm dealing with a binomial distribution. All right, so a binomial distribution has conditions. There needs to be a fixed number of trials. Fixed probability. Independent events. And 2 outcomes. If these 4 conditions are satisfied, then the distribution is binomial. And if a distribution is binomial, it could also be treated as a normal distribution. All right, so we're able to verify normality by establishing that these conditions are true. All right, so the first one, fixed number of trials, that would be 14 births. So that's a check. We have 14 births. Fixed probability, they gave it to us. That's probability of female is equal to 0.508. Independent events, well, what that means, and just going back in the notes, independent events occur when the probability of one event occurring has no impact or no bearing on the probability of another event occurring. All right, so if it's basically saying if the first person, let's say there's 14 births, I'm assuming it's in a hospital ward, maternity ward, where there's a bunch of different folks having kids, and it turned out that there were 14 births. It's not necessarily one person giving birth to, I don't even know what you'd call it, like not triplets, not octuplets, but 14 plits, so they just keep coming and coming and coming, so independent events would be the chances of the first person having a female would not impact the chances of the second person having a female child, or the third person, or the fourth person, and so on down to the 14th person. All right, so that's a reasonable thing to assume. So this is an assumption because we don't know that for a fact, but it's reasonable to assume that it's the case. All right, and then the 2 outcomes, that's more academic. All right, so it's also an assumption. All right, and since this is related to the 2010 census, it only had the two genders, so we're just kind of going with that information. All right, so we can assume that it is definitely a binomial distribution. All right, so this would be a yes, because those 4 conditions were satisfied. All right, now that we know that, it allows us to use the binomial functions in the calculator. All right, so let me take you to that. I go into the toolbox. again, if you're starting off from scratch, like right from the beginning, it lands you here. You scroll down to probability, distributions. So in the NumWorks. Probability, or toolbox really first. Probability. Distributions. And you'll see an option for binomial. And then select the one that says binom PDF. All right. So that would be binom PDF. M and P. All right. So the M value is the event that you're looking for. All right. So this is a particular event. The N value is the number of trials. And the P is for probability. All right, specifically probability of success. All right, it's kind of tricky territory because we're defining a success as the birth of a girl or female. That in and of itself isn't that tricky because you could define success as whatever you want, right? But in cases where you're dealing with, let's say, a life insurance policy, a successful outcome would be if you were able to cash in on your life insurance policy, which would mean you died, which doesn't sound very successful, right? So it's a matter of perspective. All right. So you could define something as a success or a failure, but you may have a different opinion from somebody else. It's really, what are you rooting for and what actually happened? All right. So we would select binom PDF, MNP. I must have hit the OK button like 7 times before it actually took. So the quote unquote success would be 0. So I'm going to work my way right through this table. All right. So the number of trials was 14 and the probability of success was 0.508. All right. Calculator accepts decimal values. So if a probability is given as a percentage, you got to convert it over to decimal. All right. So I hit OK and it'll give me this disgusting decimal, which I can round and try to squeeze into that tiny table that I included. So I'll take that as a typo because that table should be much wider. All right, so this was supposed to be a 37 and that table should have been wider. So I'm gonna have to try to smidge this in there. All right, so I'm gonna write it in its true decimal form, or at least approximately. So 0.0000487.
So what would you do? Binomial parentheses, basically 0, 14, 1, and then 0.59. You'd have to do that for the whole list.
You'd have to do it for the whole list. Yeah. There's a method that you could use in the stat editor that I can try to show you because it's kind of aggravating because it doesn't always work. I'll show you real quick. If you put in the numbers 0, 14, 0, 1, 2, 3, 4, 5, 7, 8, 9, 10. There's shortcuts to this too. It's only 15 values, so I'm just going to pop it all in. All right. Now this is the part, so typing in numbers from 0 to 14 that's not the part that's challenging. The part where you actually have the NumWorks calculator figure out all the probabilities in one shot, that can be a little dicey. So what you would do is you go on to value, sorry, I got a little click happy here. Go on to value V2, hit OK. There's an option to fill with a formula. And it gives you some default values here, but none of those are useful for us. All right, so what you would do is you go into the toolbox. So hit OK to select fill with a formula, then go into the toolbox, grab this. Now, the particular values are stored into V1. So I would select, I hit the wrong thing. Shift alpha. The V is right above the division symbol. 1. And then, like the same structure as we did over here, everything else would be the same. The N value, the P value. So the N value is 14. The P value, the probability value is 0.508. And this is really the moment of truth. It's either going to work or it isn't. It did. I'll run it through again in a second because I'm actually surprised it worked, because the last 17 times I tried doing something like this, I got an error message. But this is how you could get it all in one shot. And then it would just be a matter of just writing this information down, which in and of itself is a little complicated. All right, because there's so many values to account for. But let me do that again. And also I'll just write a summary of what I'm doing. All right. So you would type in all these values, go into V1. I'm going to clear this out. All right. So all those values go into V1. You go to, so for this column, go to value V2, like right onto it, and hit OK. Select fill with a formula. Empty. All right. Sometimes the ones that are preloaded will be useful for you, but most of the time they won't be. I've been in contact with the NumWorks people about updating it so that you could actually save a formula that you write, but so far no good. All right, so you hit OK. All right, so empty, then OK. So now in your home screen, the field at the bottom of the screen, you see V2 equals. All right, so we bring up the Binom PDF. Type in V1. We get the V by hitting Shift Alpha, division, and then, just the number 1 after that. The comma key it's a comma key. It's right below the toolbox. All right. So in there, I would type in so hit the comma, then type in the number of trials, so 14, and the probability of success 0.508. Close it up, and then hit either OK or execute. All right. So again, I'll just carry out the process. So into the toolbox, Binom PDF, that's this whole description over here. Take the first option, type in V1, so Shift Alpha, division. If it doesn't bring up a capital, it's probably because you either didn't, well, most likely you didn't hit Shift. So Shift Alpha, division to bring up the V, type in a 1. 14 is the number of trials. 0.508 would be the probability of success on any one trial. Once you have this in there, you hit OK or execute, and it'll populate the entire table. Sorry, the entire list with the appropriate values. All right. So that's what I'm going to do. And then it's just a matter of jotting this information down. All right. So that's the fun part. So 0.000704, 0.00472, 0.0195. Numbers get more manageable as you get further down the line, but then it'll become unmanageable again. So 0.0554, 0.114, 0.177, 0.209, 0.189, 0.130, 0.0671. Oops. I hit the right arrow instead of the down arrow, and now I'm just kind of locked. Oh man, this is getting crazy. All right, come on. All right, so 20252, 0.00651, 0.00103, and then one with some scientific notation that I'm just going to put in ordinary notation. So 0.0000762. All right, so those are all the probabilities associated with the particular outcomes. All right. So yeah, it's not ideal, but at least
So
something.
question,
Sure.
why we are like you're putting the answer like 0.000762 if in your value B2 is giving you a different one? I got confused a little bit in that part.
Well, because it's scientific notation, you see at the end where it says E-5.
Mm-hmm.
That tells you to move the decimal place to the left 5 units.
Okay, got it. Got confused with that. Thank you.
No problem. All right, so now we have all our outcomes, and to the best of my knowledge, there's no way to put it into a frequency column, which is kind of aggravating. I'm going to try something else real quick. Just bear with me. Yeah, don't do any of this until I prove that it'll work. And then I'll show you, if it does work, then wonderful. You hit the wrong button sometimes and it just takes you out of where you want to be. Okay. Yeah, it does work. Okay, I'll show you. All right, so this is just an extra layer to this. Just this part that I'm about to show you, it's to avoid having to type all of these numbers into this column. All right, because these are really relative frequencies for 0 through 14. Okay, so they need to be in the same column, but the thing is you can't apply a rule. Like if I tried doing everything I did with the binomial thing in N1, I'll just show you real quick. So dang, things just moving on me. Oh, of course, now it works. Jeez. Oh, it's so frustrating. I swear that didn't work the last 5 times I tried it.
It
Ugh.
always is. It never wants to work until you're in front of everyone else.
Yeah, I mean, honestly, I guess that's better than the alternative where I think that something is going to work. And then I'm like, hey, look at this cool thing that I'm about to show you, and it doesn't work. So I guess this is better than that, but it's really just frustrating. All right, so well, I learned one thing just now, and it'll be to our benefit. It's just we're going to do this computation one more time. So this goes into, instead of value V1, we're just going to do the same thing that we did before, just in the frequency N1. All right, so I'm going to take it from scratch, do it one more time. My loss is your gain in some cases. All right, so we typed in all the values in V1. So we would go to frequency N1, hit OK, select fill with a formula. So all the remaining steps are still the same, except this is going to be N1. All right, so fill with a formula, empty. Then we go to our toolbox, select the first option. All right, all the values that I want here are in V1. So I do that again, V1, 14.508. All right, so same process, except it goes into N1 instead of V2. All right, when you hit OK, it populates the whole list. And then from there, you go into stats. And find the mu value and the sigma value. All right. So you have all this information in here. You go to stats, and right on down the line, you'll see the mu. That's population mean, 7.112. And 1.871 is the population standard deviation. All right, so we get the mean and standard deviation. We can look at the graph too if we want. In this case, I mean, we use the binomial distribution, which is a special case, or at least it models a normal distribution. So, I mean, we kind of already hopefully know what it's going to look like, but if you're not sure, you could always go to the graph, do a histogram, and it'll show you, you know, it makes up its own bounds, but that does have a normal look to it, roughly symmetrical. Most of the values are in the middle. So if you're interested in that. So yeah, we could say, is it still approximately normal? We could say yes. All right. But then we want to know, is it unusual? I know it got a little messy here, but ultimately the question is it unusual to get 11 girls among 14 births? All right. So now that I know my mean and standard deviation, I would use the rule, right? The usual unusual rule, it's on page 37, is mu minus 2 sigma, comma, mu plus 2 sigma. All right, that's the same idea as the X bar minus 2s and the X bar plus 2s rule that we used in the first unit. But because we're dealing with populations, it's mu and sigma instead of X bar and S. All right, so again, in the stats menu is where you'd find this information. Just look for the one that says mu and the one that says sigma. All right, now we don't really need the precise value, so I'll go into the home screen and run the numbers. But if you're not sure about the notation, this one says mean and standard deviation, but this pair says sample mean and sample standard deviation. So as long as you know we're working with a population of values, you would know that you don't want the ones that say sample. All right. So then I'm going to go to my calculation. 7.112 minus 2 times 1.871. And then same deal, just with a plus sign. All right, so 3.5 10.37 to 10.854. This is the usual interval. So usual values. Any number that falls outside that interval is going to be unusual. So we can conclude, so therefore, 11 girls would be unusual. And like I said, if you verify that what you're dealing with is a binomial distribution, there's a lot of fluff that you can cut away. Like I don't need, if I know it's binomial, I don't need a picture to help me determine if it could be modeled by a normal distribution. Is it still approximately normal? Yes, because if it's binomial, it's approximately normal. All right. But it comes down to these conditions: fixed number of trials, fixed probability, independent events, and 2 outcomes. When you look at a particular scenario, those are the things that you're looking for. If it turns out that you've satisfied all those conditions, then you're dealing with a binomial distribution, and this would be the approach that you use. All right. Now, I can tell you, this was a challenging problem. Well, that's not the thing I was going to tell you, because I think that's obvious. I'm not going to make you come up with the data table on the test. I'm going to give you the data table and ask you to draw the conclusions based off of it. All right. So that's actually what we're going to do now. We're going to move over to the test, because the remaining topics in this unit, geometric distribution, all that stuff, they're all optional topics. They're technically part of probability, but I like to save them for until the end of the course, because we want to make sure that we get through all the mandatory topics before we get into anything that would be considered optional. All right. So let me stop this recording so I can save it.